Today's speaker is Aleksander Kubicki. He'll be talking about showing new claims for position-based cryptography using concepts of the geometry of Banach spaces. Whenever you're ready, Aleksander.
Hey, hi, good afternoon, everyone. First of all, let me thank you for the invitation and thank you very much for the interest in my work. And the work that I will be presenting today is based in the preprint that you can find in this arXiv reference, which has the same name as this talk. Essentially, this is joint work with Marius, who is working at Urbana-Champaign, and Carlos and David, who are both in Madrid. Just a question, can you see my mouse? Just to, okay, perfect. So I can point things. Great. So, okay, I structured my talk in 4 main sections. First, I will introduce the basic setting of position-based cryptography. This first, little longer section. Then I will talk about the concrete protocol that we analyze in this work. And then in the third section, I will try to explain what are the main ideas behind the proofs of our results in this work. The talk will conclude just pointing out some questions that remain open and which are suggested by the results that we obtained. Okay, so let's talk about position-based cryptography. So in this setting, we can consider 2 agents, a verifier and a prover, who try to communicate in a secure way between themselves. And in order to establish security, the verifier would like to certify the identity of the prover. The main idea in position-based cryptography is solving this identification problem using the geographical position of the prover. So somehow we want to use the position of this agent as the credential of its identity. And once the prover shows that it is indeed in this position, the verifier interacts with the prover as if the identity was verified. In the simplest case of one-dimensional position-based cryptography or position verification, which is the task of securely verifying the position of an agent, we have a prover that is surrounded by 2 verifying agents. These verifying agents interact with the prover, posing some challenge, and the prover is asked to solve this challenge. In order to pass this test, the verifiers after the protocol will look at 2 conditions. So the answers from the prover should satisfy timeliness, what I call timeliness, which means that simply answers should arrive in the expected time to the verifier. So if the prover take too much time in answering the challenge, then the test will fail. And once this timeliness condition is met, the answer from the prover has to be also correct, according to some public rule that is defined by the protocol. Okay, so in this setting, first we are considering just purely classical protocols in which the communication between verifiers and prover is classical. It turns out that a team of cheaters can intercept the communication between verifiers and prover, and interacting between themselves, they are able to simulate perfectly the action of a honest prover in the middle. In that way, a team of collaborating cheaters or colluding attackers are able to cheat any position verification protocol when the classical messages from verifiers to prover are classical. This somehow motivates the consideration of quantum protocols, in which now the communication between the agents is mediated by some quantum channel. So now the verifiers prepare some quantum system that is shared with the prover, and the prover is asked to perform some computation on this quantum system and return the output of this computation. We can also consider this kind of colluding attacks in this setting, and it turns out that this type of attackers are also able to cheat any position verification protocol also in this quantum domain. The main difference now, and also the main interest of this setting when everything is quantum, is that the attack that this kind of agents, dishonest agent, has to perform need to make use of a huge amount of quantum resources. Specifically, they have to use a large entangled system in order to cheat with a good enough success probability. So the main question that we are interested in now is how large or how many of these resources the attackers have to spend in order to cheat particular position verification protocols. Fixing some notation. So if we call K the dimension of these quantum systems that are manipulated during the attack, and we call N the dimension of the system that are manipulated in the honest implementation of the protocol, known upper and lower bounds for K in terms of N are as follows. So in 2013, it was shown, okay, first, the known attacks to quantum position-based cryptography consume an amount of entanglement whose dimension is of order exponential in N, okay? And in the other side, it's known that there exists position verification protocol for which a linear amount of entanglement in N is needed in order to cheat with non-negligible success probability. So we would like, so in this work, our main motivation was trying to improve on this gap, exponential gap that exists between these lower and upper bounds. We do so only partially. And what we did, in fact, is obtaining new lower bounds for this quantity K for a particular protocol that I will introduce in the next section. And what we have shown is that the amount or the dimension of quantum systems that are spent by the cheaters in order to cheat this protocol scales exponentially in N, but only when some additional assumptions are forced. So these are the drawbacks of our result. So our result doesn't close this gap in full generality, but at least allow us to go a step further and just to have some new knowledge on this setting. The drawbacks of our lower bounds that I wrote here is that these bounds are only valid for some kind of cheating strategies that we defined as smooth strategies or regular strategies. This will become clear later on. And the second drawback is that in the protocol that we analyze, the systems that are shared between verifiers and prover are not only quantum, are a quantum classical system, and we will not analyze what happened with the classical part of this input, which is of much larger dimension than the quantum part of the challenge. This also will become clear in the next session, but this is also somehow a limitation of our results. For another result, very interesting about this setting, or a similar setting at least, you can check this other work, which was that appeared concurrently with the paper that I presented today, and in which they prove also some lower bounds, which are in fact stronger than our, but in a setting which is similar to us. Okay, so let's now take a closer look at the action of the agents in general position verification protocols. So I recall you that in this one-dimensional case, the verifiers send some challenge to the prover, and the prover has to answer to this challenge meeting these two conditions. Okay, if we try to look at the action of the honest prover in a space-time diagram, we can sketch the following picture. So first, the verifiers start the protocol sending some messages, which can be quantum in general. After the reception of these messages, the prover it has to compute some, for simplicity, unitary or some quantum operation on this input, and then immediately the prover has to reply to the verifiers. Okay, so this is the ideal action of a honest prover who tries to pass this test. So let's take a look now at the action of colluding attackers. So again, the protocol starts sending some quantum messages from the verifiers. Now these messages are intercepted by a couple of attackers who now are able to implement a couple of local operations, quantum operations on these inputs. After this, they are still in time to share a message simultaneously between the two provers, acting again locally on the quantum system that they hold. And after this second round of operation, they are still in time to reply to the verifiers meeting this timeliness condition. So this is essentially the structure of the action of cheaters in this setting. Since this structure will be quite important for us, let me just put some names on the actions, on the local operations of these attackers. So let's call from now on VW and tilde V tilde W to these 4 local operations. And let's call, okay, sorry, this will be called phi, I think, later on. And this is simply an entangled state that the attackers are allowed to share before the protocol starts. Yeah, exactly. Okay. So from now on, I will be referring to cheating strategies simply as tuples of 4 local operations, which can be thought to be unitary, just for simplicity, and some entangled resource state, which will be called phi. Okay. In order to cheat in a position verification protocol, what the attackers want to simulate is the ideal action of a honest prover. So we can say that the goal of the attackers in this setting is trying to mimic any unitary, U, global unitary, with this structure of local unitaries mediated by a round of simultaneous two-way communication. So now let's particularize the setting that I introduced to the protocol that we analyze, which is called Grad. So first, let me define the protocol. In this protocol, we fix some natural number n, and the verifiers start preparing in one side some quantum state psi, which is defined like this line, but the details here are not so important. And on the other side, the verifier sample a sign vector with n-squared coordinates. Okay, so it's a vector, a classical vector, whose coordinates are plus or minus 1. Okay, so there's from one side, the prover receives this classical information, this classical epsilon, and from the other side, the prover receives a quantum system, which is part of the psi that was prepared by the verifiers also. The goal for the prover is implementing this diagonal unitary, which is defined by this sign vector, epsilon. Then, after the reception of these 2 pieces of information, the prover has to implement this diagonal unitary and just reply one part of the output to the left and the other to the right. And as I said before, now the verifiers just check that timeliness is fulfilled. This means that the answers from the prover arrive in time, and the correctness, which means that the diagonal unitary U sub epsilon was implemented correctly. They essentially perform a binary dichotomic projective measurement just to ensure that. So now let's look at colluding attacks for this particular protocol. And again, just attackers here just intercept communication from verifiers, interact between themselves, as we have shown before, and then reply to the verifiers with some quantum states. An informal statement of our main result is that when the action of these attackers fulfills some regularity condition that I will define in a minute, then they are able to cheat with a probability large enough only if the dimension of the system, the quantum system that they manipulate, scales exponentially in the size of the protocol, which is n, which is essentially the size of the quantum systems that are manipulated on the honest implementation of the protocol. And this is the main result that we want to prove from now on. Okay, so I recall you that the structure of the action of the attackers here follows this picture here. And now I particularize this picture to the protocol Grad. So from one side, the cheaters receive this classical input epsilon. And from the other side, they receive the one part of this vector psi that was prepared by verifiers. Okay, then when they receive these two pieces of information, they can apply for local operations, VW and tildes. And these three local operations, so this one, can depend arbitrarily on the classical input epsilon. Well, not arbitrarily. This is what I'm going to restrict later on, but in principle, these three unitaries can be chosen differently for each input epsilon. So now our cheating strategies are characterized by tuples of local unitaries and vector phi. And now these unitaries are also listed for different values of epsilon. That's all. So the key idea here is that this kind of tuples can be reinterpreted as assignments on the Boolean cube, which assign to each point of this manifold a vector in a given Banach space. Okay, so this is like the general idea. Later on, I will give you a particular construction for these functions. But now let me sketch how the general argument works. So the first thing that we need, once we make this connection, is relating the cheating probability that is attained with a given strategy S with some value depending on this function. And what we are able to do, in fact, is relating this cheating probability with the expected norm attained by the images of this function phi. Okay. So this allows us to translate the study of this position verification protocol to the study of functions that takes elements in the Boolean cube and gives vectors in some Banach space. Once we have that, we turn into the study of this function phi, and for that our main technical tool is an inequality that is a consequence of a known inequality due to GSPCM. And this inequality allows us to relate this quantity, which is essentially the cheating probability attained by the attackers, with two terms in the right. So the first term will be dealt with later on, and the second term is the one that is related with the geometry of the Banach space appearing here, and also with some properties of this function phi. So in particular, this sigma sub phi will be related with the regularity properties of this function, and this second parameter will be related with some geometric property of x, which is called the type 2 constant. So first, about the regularity of phi, we will define this parameter sigma essentially as the two sum or the two norm of the gradient, the discrete gradient of this function phi. Okay, the expected value over that. This equality here is just hiding logarithmic terms and constant terms that are of no interest for us. In order to gain some familiarity with this definition of regularity parameter, let me consider the example of linear functions. So imagine that in our Banach space X, we take n square elements in the unit ball. Now I can define a function naturally in this way. So simply as the linear combination of these elements in the unit ball of X. If the normalization is properly put here, then we can compute directly the discrete derivatives of this map. And then we obtain that for this kind of ideal functions or very smooth functions, this parameter phi scales as some logarithmic term over n. Okay. And somehow this kind of functions will represent the ideal case in which we are able to get powerful lower bounds on the resources of the attackers. Okay, so strategies whose associated function phi has this kind of behavior will be referred as smooth strategies or strategies that are regular enough. Okay, so I recall you that in this inequality here, we have this regularity part in one side, and in the other side, we have this two-type constant of X, which I'm going to explain now. The type 2 constant of a Banach space is simply the smallest constant that satisfies this inequality for any sequence of elements in the space X. Okay, again, maybe the details here are not super important. I will give you an example now that I hope will clarify a bit this obscure notion. But just to complicate a little bit the thing, we also need the notion of type 2 constant with n vector, which is precisely the same thing, but restricting the cardinality of the sequences that are considered in the definition to those with at most m elements. Okay. Again, this is not super crucial that you get all the details here. So let's take a look at the example of one of the most canonical Banach space, which is the case of Hilbert spaces. Okay, in Euclidean spaces, we have the important fact given by the parallelogram law that given two any vectors, we know that the square root of the norms of the sum and the difference of these two vectors fulfill this parallelogram law. Okay, rearranging this factor of 2 in this equality, it turns out that we can rewrite the equality precisely in the form that appeared in our definition above. And in fact, this is a proof that the type 2 constant with two vectors in this case of a Hilbert space is precisely 1. Okay, and in fact, having this equality is up to constants is a fact that characterizes Hilbert spaces among all the category of Banach spaces. With a trivial generalization of this argument, you can in fact show that the type 2 constant of Hilbert spaces is in fact 1. Okay. So in this sense, you can understand type constant as a parameter that informs you how far is from the Euclidean geometry, the geometry of the Banach space that you are considering. Okay. Do you have any question at this point or up to now? Is it everything more or less clear? I hope so. Well, okay. Let me recap a bit. So we have connected cheating strategies for our position modification protocol with functions on the Boolean cube. Once we have this connection, I claim that I'm able to prove some relation on the mean value of the norm of this map with the cheating strategy that the attackers attain with the strategy that we started with. After that, we started the study of this value here using some inequality in which the notions of regularity of the function or tied to constant of the space on the underlying space appears. So now let's deal with this other factor here. I will not do the details here, but the fact is that we can prove a technical proposition that allows you to just forget about this first term. So we are able to prove that this first term is always smaller than 1. Okay, so we can just forget of the first term and concentrate on this second part of the inequality. Okay, this is a constant that I hidden before. I just forgot to hide here, but it's not important for us. So okay, so once we are at this point, the only thing that remains to be done is to study what is the regularity of a given strategy, this parameter sigma, and what is the type constant of the Banach space that we are considering. So as I said before, this is just the general argument. And of course, this argument depends crucially on what is the choice that we made for this function phi. So this is the following thing that I'm going to do. A first choice that we consider in our work is defining this function here based on the second round that is implemented by the attackers in their attack. So let's just forget about this part of which pertains to the first round of operations of the attackers. The V will, okay, which is not often important for us. And then we define some map which depends on this operations tilde V until the W. Yeah, okay, an important detail here is that once you construct this map explicitly, it turns out that the right norm in the image space is the one given by the infinite Schatten class. This is simply the Banach space of bounded operators in a k-square dimensional Hilbert space. That's all. Okay, so this is you can think of this space as the space of k-square dimensional matrices with the operator norm. That's all. Okay, and it turns out that if you choose this norm here, you can obtain the lemma that relates the cheating probability attained by this strategy S and the expected value of the norm of this function here. A good news for us here is that we in fact know what is the type 2 constant of this space, and it turns out that this type 2 constant scales logarithmic in the dimension. And this allows us, okay, again, yeah, exactly. Starting in this inequality, we put here the information about the type 2 constant of the space that we have, and now we just impose that this parameter is well behaved. That's all. That's all we can do. So the first part of our main theory is just an upper bound for the cheating probability that depends on this regularity parameter, which will be set now. Yeah, okay, so an alternative construction for this phi is now looking at the first round of the strategy that the attackers perform. So again, now we forget about this tilde part of the strategy and focus on these three elements. With this definition for the image of this function, and with a more cumbersome choice of Banach space here, of norm here, we again are able to establish this link with the cheating probability in position verification. And in fact, we are also able to estimate the type 2 constant with n squared vectors, which is all we need here, as this upper bound. Okay, this is used. This is obtained using some some tools from Banach space theory, essentially some tools developed by PZ also in order to study this kind of type problems in tensor norms, projected injected tensor norm Banach spaces. And this is how we are able to obtain this bound. Okay, the details can be checked in the preprint. But once we have this bound for the type 2 constant of this space, we can obtain a similar bound as before, but in terms of this other regularity parameter that is related with the regularity of this second function phi. What these two previous statements tell us is that if we have a strategy, a cheating strategy that fulfills one of these two regularity conditions, then in order to cheat with probability close to 1, the cheater have to use quantum system whose dimension must scale exponentially linear, okay, which is the size of the quantum system that the honest agents in the protocol manipulate. This is the main result. So let me, I still have time. So let me tell you about a third possible choice for the construction of this function phi, and it's the one in which we just forget about the elements that are epsilon dependent in the strategy, and construct a function phi which is linear in the sense of the example that I gave you before. Again, we are able here to identify the right norm in order to establish this connection with the study of position verification. But the problem now, okay, so this is what I have here. So we are able to prove this lemma with this space here. As I said, this function now is linear in the sense of the example before. So this means that by construction, this function is regular enough. And also by construction, the function is simply symmetric. So the expected value of the images is just average to 0. Following the same argument as before, this allows us to obtain an upper bound of the cheating probability given any strategy S by the type 2 constant of this converse sum space here. So in this way, we were able to translate the problem about upper bounding the cheating probability attained by attackers with the problem of estimating the type 2 constant of a given Banach space. And the problem is that we were not able to estimate this type 2 constant, but we conjecture that the type 2 constant of this space behaves in a similar way than the type 2 constant of the space that appeared before. And in the paper, we give some evidence supporting this conjecture, but it is still a conjecture, and we don't know whether this is true or false. If the conjecture were true, then we would obtain a corollary as the one before, giving exponential lower bounds for this for k, but without the need of assuming any regularity condition on the strategies. So this would be a very interesting improvement on our results. But this is all that we have from now. Okay, and with that, I will finish my presentation just with some comments at the end. So as I said during my talk, our results have some limitations. The first one is that, well, one of these limitations is that we have not considered what is the role of the dimension of the classical systems that are manipulated during the protocol. And in fact, even when our lower bounds are exponential in the dimension of the quantum systems, the dimension of the classical systems in this protocol are exponential in this other dimension. And this means that our bounds are only linear or even sublinear in this dimension. So the good news here is that we can generalize some of the techniques and in fact some of the results that we have to games or to protocols in which there is no classical input. So recall how our protocol Grad works. So the verifier started the protocol preparing some state psi and sampling some classical vector epsilon. And then the prover was asked to implement a diagonal unitary that was defined by this epsilon. So now we can think about the following modification of this protocol. So fix in advance a given epsilon, and now distribute one of the registers of this psi from the left to the prover and the other from the right. Now we can ask the prover to implement the same unitary, but the difference now is that the dimension of all the systems that are manipulated in this protocol is polynomially n, simply n squared, right? So now if we consider the family of protocols indexed by epsilon as a whole, and we again study families of strategies for this whole family of protocols as assignments on the space on this Boolean cube, then we can again argue in a similar way as before and obtain some results under this kind of regularity assumptions. So we still don't have any definite results, but at least we can sense something in this also interesting setting. The other limitation of our results are precisely these regularity conditions that we have to impose. These kind of regularity conditions are in fact fulfilled by known attacks, known general attacks to position-based cryptography, but we have an idea whether this is a completely general feature or whether there exist more efficient attacks that violate these kind of regularity assumptions. Okay, my two comments here are that in order to, okay, one route in order to avoid this kind of regularity assumptions is just proving our conjecture about the type 2 constant of this Banach space that I showed before. But we found that we are short of techniques in order to tackle this conjecture. So it would be very welcome to develop new techniques in order to address this kind of questions. Another route to improve in that direction would be also to try to better understand what is the meaning of these sigma parameters that I introduced. So it might be the case that this kind of regularity parameters can be related with some physical properties of the strategies, but we still have no much idea about that. Okay, and to finish the talk, I also will comment on some connections that exist between the fields of position-based cryptography and other areas. The first one is a recent connection with the holographic duality between ADS and CFT that was showed in this sequence of papers, and which opened the possibility that maybe our techniques and our result might be used in this context to say something about the map that implements this duality. So in the sense that, okay, the idea behind this connection showed by Alex Meyer and co-authors is that the holographic picture of the action of the honest prover in this setting is in fact, or can be at least interpreted as an attack, as a colluding attack to a position verification protocol. So, okay, so the claims that they have is that these kind of attacks have to be, okay, the resources needed for these attacks that comes from this holographic connection must scale linearly in the size of the protocol, and the kind of result that the results that we obtain, it seems to contradict this. There is no contradiction because we need some further assumptions and so on, but it seems that there is a possible route to maybe study some properties of this kind of holographic duality by means of the techniques that we use here. But this is highly not clear how this could work, let's say. So a final connection that I would like to point out here is that we have related these kind of questions about position verification, position cryptography, with some properties of some mathematical construction, which are tensor norms of Banach spaces. And maybe studying position-based cryptography would be also very interesting if studying position-based cryptography will give you some new information about this, the properties of these spaces. But still, I had not much idea about that. And that's all I had to say. So thank you very much for your attention. I hope that you enjoyed.
Great, thank you. So I'm going to go ahead and stop the recording.